This is a short summary for Chapter 10, which was focused on free type constructions. I begin with looking at the interpreter pattern. I explain how the interpreter pattern translates programs into case classes, that is, into data structures that represent unevaluated expression trees for the program. An interpreter will then run the program. I show that simple DSLs work, but they're not type safe. In order to make them type safe, you need to use type parameters and certain values of the type parameters in your DSL operations. I show that if you want to reuse previously computed values and choose the next operations, you need an operation called bind. And the operation called bind is exactly the same as a monadic flat map, so therefore you need your DSL to be a monad. I show how to refactor a DSL into a general part that is common for all programs and a part specific to an application, and that gives us a free monad construction. I show that if you run the free monad into a different target monad, you can do error handling, and this shows the flexibility of the interpreter pattern. I summarize how to construct a free monad DSL out of a type constructor. Now, the laws of the monad do not necessarily hold for the monad DSL, but they do hold after interpreting into a target monad. In other words, the monad law violations are not observable. I explain why the word free is used for the free monad. I show what a free semigroup is and how mathematicians can define free operations. And these operations do not have any computation inside them. They encode the full unevaluated expression tree. And I explain what a reduced encoding is, which is an encoding that is simplified from the tree encoding by using the equivalence laws. I give an example of a tensor product as another free construction. Then I show how to implement a free semigroup. I show the tree encoding and I derive the reduced encoding. I do the same for the free monoid. I show what happens if we want to map a free semigroup to different target semigroups. And the run operation will satisfy a certain naturality law, and the functor law will be also satisfied. I show that if you want to combine different target semigroups, then you can refactor the code using typeclasses, and you can represent the semigroup instead of case classes by pieces of the run method. And after this refactoring, we arrive to the church encoding. So this motivates why the church encoding can be useful. I show the general definition of a church encoding, which is this type expression for any type A. I show how church encoding works for disjunction types and why this allows you to implement the church encoding in disjunctions in languages that do not have disjunction types. I explain in detail why is it that this type expression is equivalent to the type A, and prove that this is so in terms of observable equivalence. Then I start with encoding a free functor. The free functor can be encoded in a tree encoding like this, and once you do that, you need to have a case class that is parameterized by a type parameter that is not visible in the parent type, and that gives rise to an existentially encoded type, which I explain in more detail. I show how the existential type works and prove the basic equivalence, which is more generally like this. It is a basic equivalence of existential type and an ordinary type. So this can be seen as an existential encoding of the type A, just like the church encoding of a type A. So I prove this equivalence. Now we are ready to do the encoding of a free functor. I show the free functor in the tree encoding, and I derive the reduced encoding by reasoning about the tree encoding and its equivalences under the laws of the functor. Then I want to do the church encoding of the free functor. This is now much more complicated because of all the type quantifiers that are required. So I take a little aside to explain the recursive types in the church encoding. The church encoding makes them non-recursive, at least on the surface, because it replaces the recursive use of the type in the recursive definition by the use of the type X, which is under the universal quantifier. I explain why this works, and I give examples of encoding a list of integers, which is a recursive type, as a church encoding. I also then look at church encoding of a type constructor, and I figure out how to encode the different type quantifiers necessary for this construction. And I show there are two different type quantifiers required, and I show how to encode them in Scala. Finally, I combine these two in order to show how to do a recursively defined type constructor in church encoding. And as an example, I give the list as a church encoded type. I then show that church encoding is very easy to use with type classes. For example, the church encoding of a semigroup can be seen like this. And this shows you directly how to generalize to an arbitrary type class, as long as the operations of the type class or the methods are given by this type, where C is a certain functor that I call the method functor of the type class. In that case, I call this type class inductive, and I explain why it makes sense to call it that. It is because you define the type class values by induction from previous type class values by applying its methods. Then I show the general formula for a tree encoding and the church encoding of a recursive or non-recursive type class. It doesn't matter if the type class itself is defined recursively or not. This formula is general for an arbitrary type class C over a type Z, or type class C instance of a type class generated by a type Z. And I show how this works also for type constructors. The properties of free type constructions follow from our intuition about what they should be doing. These are the four main laws, and I formulate the questions that will occupy us for the rest of the lecture. I summarize the recipes of constructing a free type class instance for an arbitrary type class with given methods. As long as it is an inductive type class, then we translate these methods into case classes. We might have to use existential type parameters in some of these, and we derive a reduced encoding and the church encoding. The properties of inductive type classes are that all inductive type classes have a free instance defined like this. The product and the function giving you an inductive type class is again an instance of the same inductive type class, but this is not true for disjunction or a product with a constant type. And this reminds us of what we have seen with all the standard type classes, such as functor, monad, applicative, and so on, where the product of type class instances was again a type class instance, and the function from a constant type giving a type class instance, it was again a type class instance, but not necessarily coproduct or product of an instance with a constant type. That was not necessarily an instance of a type class. And that is because all the standard type classes are inductive. I show examples of type classes that are not inductive, and so they cannot be tree encoded into free instances. And one of these examples is this type class with two methods, and another is traversable. And then I indicate what is a co-inductive type class, but this is beyond the scope of this chapter. I come back to a free functor and a free contrafunctor and other free type classes for type constructors. And I show how to derive tree encoding and reduced encoding, and I indicate how one might have used a free contrafunctor in practice. The next type class is free pointed functor. I do the same procedure starting from the tree encoding and deriving a reduced encoding, and then I see what happens when the type constructor f is already a functor, how the pointed functor is greatly simplified. And I point out that if the type constructor f is already a pointed functor, then a free pointed over f is not the same as f. It was, however, the same for the free functor and the free contrafunctor, but that's a special property of those foundational type classes. I go then through the same procedure for a free filterable. The filterable type class was explained in chapter 6, and I do the same for a free monad and the free applicative. I make a note that what people call these days a final tagless style of programming, it is nothing more than the church encoding of a free monad over a constructor f. And I point out that it is better to think about these things in terms of a free type class over a type constructor encoded in a certain way, because this shows you the freedom you have of choosing a type class, choosing one or more type constructors or one or more type classes, and choosing the encoding for that. You can choose different encodings and different type classes. So final tagless is just one particular choice of an encoding over one particular choice of a type class over a type constructor. The free applicative functor goes through the same procedure. I also show what is a free zippable, that is an applicative without pure. And I proceed to derive the laws formally of the free type construction, starting from the tree encoding and going through the derivation and formulation of the identity law, the functor law, the naturality law, and the universal property. I also show a formal definition of what it means for a function to be type preserving, type class preserving. This is this diagram. Then I show how to combine different generating constructors in a free type class. I show why that is equivalent to taking a disjunction of the generating constructors and constructing a free type class instance over that disjunction. I show how the church encoding gives us a way to encode very easily and concisely a free type class instance over any number of constructors and for any inductive type class. As long as you know the functor method, the methods functor for the inductive type class, you can formulate the church encoding like this, or even if you don't know that, you can have this general formula, which gives you a code that's much easier to maintain. And this works for any type class C and for any number of generating types Z. And then I show how to combine different type classes in a single free instance. I show that the composition is not necessarily a good way of combining them. And the better way is to do disjunction. And again, the church encoding gives you an easier way of implementing disjunction. And also, you can just add different type class constraints here into this formula. And the result will be a general formula for the church encoding of any number of type classes with any number of generators. I give an example of combining a functor and a contrafunctor, which is maybe counterintuitive, not very useful, but it's an interesting illustration that you can combine anything. Even if those properties are contradictory on the surface, you can still combine them in a free type class. A second more useful example is combining a monad and applicative functor in a single type class. And I show how to run the result through the future monad so that the parallel execution is preserved for the applicative operations and the sequential execution is preserved for flat map operations. And I give exercises. The sample code for this chapter gives implementations of different DSLs, monoids, free monoid, free semigroup. It shows 4 different implementations of free functor with 4 different encodings. Only one of them is not stack safe, which is this one. Others are stack safe. I show how to derive a church encoding for the different type constructors we have seen, and show the general derivation of a free instance of any inductive type class in the tree encoding and in the church encoding of the tree encoding. I show all the examples in implementing the free type classes. I prove the laws of the tree encoded free instances of inductive type classes for an arbitrary type class. I show how to combine 3 different operation constructors in a free functor using disjunction and using the church encoding. And I show how to combine a free monad and a free applicative functor in a single type class and give a running example running it into the futures.